classical communication. So basically, as we saw, like the general communications, like you have your message, you have your encoding, and after you have your channels. External, that's separation between Alice and Bob. Here I have Bob. And here we have our decoding, or for sure we have M prime, thanks to a POVM that we will measure. So yeah, Alice selects messages, M from 1 to M. So I suppose like Alice like is a satellite and she wants to set its color like red, blue, or red, blue, green, yellow. And she wants to send from her satellites like Alice and prepare some state and transmit it over some independent channels. So basically, yeah, we can like call it like M being like this, and each of them being a message. And so transmission, it just if we take like stray photons, like because there is like some rain, for example, that can destroy the signal. So Alice must send more than one photon, let's say three. She create an entangled state with three photons for red because she wants to send red. And so it goes through the channel. And so Bob should measure it with a POVM. So Bob has like, let's say, have POVM for the red, for the green, for the yellow, for the blue. The probability of success of measurements of M prime, which is red, knowing that M is red, is just equal to the trace by Born rule of its POVM about red multiplied by the new state after going through the channel being equal to 0. So what we need to know also is that the error for having red is like, let's suppose like 5%. So let's say like it's equal to 5%. Like you can say like it's 5% for red, it's like for green it's like 8, for blue it's like 4%, and for yellow it's like 10%. And so yeah, the probability of error maximal will be like 10% for the yellow. And so let's suppose like we want 12% of success, like say, let's say like we want like epsilon being equal to 12%, and everything is validated because it's inferior to 12%. So yeah, basically we have like our channel would be equal to 1 over 3, which is the number of photons, multiplied by log of 2 of 4, which is 2 over 3, beat by utilization of the laser. And so yeah, that's it. That just show how Alice show a container with code and Bob an intelligent measurements to, so Alice with entanglement and Bob with a good POVM to have like the best possible classical capacity, no matter the noise channel. So yeah, we just maximize, like take a big number of photons. Like we try to put the maximum of bits by photon, but trying that Bob still have the exact information. So the classical capacity just the maximal speed of transmission of classical information through a quantum canal with a low probability of error that we can have using some states that are long enough, like having a number of qubits, a number of photons in our case, where you can get the maximum of bits for it. So yeah, basically that's it about it, and and yeah, I think it's the main important that we need to know about. So in the definition of the classical capacity, we define it like this, like that. So yes, we just want the premium of all achievable rates for classical communication, and so we define it with a dB like C, which will be attainable if there is a code for like it's less or more equal for a little marge delta or epsilon, or I don't know this letter now. So any error for any error problem, conditions that we utilize a sufficient number of photons to encode all the bits into it. So a classical capacity just the biggest burn of all debits, the best information rate in a way, like the best transmission of information you can have. Like not to minimize the number of photons because we want like we can have error, but like trying to have the maximal quantity of classical bits that we can say by photons, and see after trying to use a lot of photons to encode them all together, and after there will be a joint measurement made by um, by Bob to destroy the noise. And yeah, if you like take the photons like big numbers, you can like destroy the noise, and that will be cool. So yeah, it's just the optimal rate that you can have, maximal classical bits that we can extract by utilization of a canal with a error which is null. But we have the condition so to have a big block of untangled photon states, for example.